Hello everyone, welcome to Helm of Science. We had already started with the introduction to organic chemistry. Today we will be basically discussing about the basic syllabus oriented part of the chapter, which is important for your upcoming board exams. Okay, so before we start off with the discussion, I would like to apologize from my end for being so late in uploading the next video for the same chapter. Hopefully, this video will help you out, and I hope that it has not been very late. Okay, so let's start. Firstly, the topic we shall start with is homologous series. Homologous series. Now, what do you mean by the term homologous? Homologous basically means difference by a difference by a CH2 group. Now, what do you mean by that? Let's take an example for better understanding. Now, let's begin with supposing I have taken something from the alkane series. Like suppose the first member of the alkane series. Now, how are we getting the first member or the second member? We'll discuss it later. But for now, just consider whatever I'm saying for instance sake. Later on, you will get to know that how we are deriving the first or the second member for that matter. Okay. So the first member of the alkane series. Now, what is an alkane? Alkane is basically the compounds having single bonds or the compounds which are saturated. Okay. There will be an in-depth discussion to all of these in the upcoming classes. But now just I'll give you a brief introduction. That is, alkanes are substances which have single bonds and they are saturated compounds. Now, what do we mean by the word saturated? Saturated means, if you remember in the first class, we had talked that carbon can only form 4 bonds, right? So, if carbon can form 4 bonds and alkanes contain single bond structures, suppose for CH4, this means all the hands are occupied by H entity, right? So, if all the hands are fulfilled, that is 4 of the hands of carbon are satisfied by hydrogen, then there is no scope for the entry of any other new group into the moiety, into the molecule. So since we cannot include any other new group to this existing molecule, that is CH4, that is why compounds like alkanes are called saturated, which means they have got the maximum valency fulfilled. If you want to correlate the word saturated, let me give you an example. If you take a glass of water, for instance, right, and you start dissolving sugar in it, sugar or salt, anything for that matter. Suppose we start dissolving sugar, okay? Then initially it will get dissolved. That is, you will not see any residue or any kind of sugar particles at the bottom of the glass. Then if you dissolve a little more, that will also get dissolved. And this way, there will be a time when you will see sugar is not getting dissolved in the glass or in the glass of water anymore. That is, the amount of sugar which you are trying to get dissolved will actually be lying at the bottom of the glass. So now what is that? That means that the glass of water is already saturated with sugar particles. That is why when you are trying to dissolve more of sugar, it is not getting dissolved. Similarly, for CH4 or alkane moiety, to be talked in general, since all of its hands are fulfilled by the maximum number of bonds that carbon can form, so we cannot include a new compound or a new atom into it. That is why alkanes are referred to as saturated. The concept is the same like the glass of water, right? Okay, now this part we'll discuss a little later. Now coming back to homologous series, Suppose I have taken CH4. So the next member, this is the first member of alkane series. Okay, this is the first member of alkane series. Now suppose I want to move to the next member. Okay, so what we will do is, to move to the next member, we will be adding a CH2 group to the initial molecule, that is CH4. So what do we get? We get C and C, so 2C, that is C2, and H4 plus H2, that is H6. So the second member is C2H6, which is called as ethane. Now why the name? We'll learn in the next classes, but for now just know that the second member is called ethane. Okay, followed by, if you want to move to the third member, then again add a CH2 group to it. That will make it 2 plus 1 carbon, that is C3, and 6 plus 2 hydrogen, that is H8. So what we see from here is, between the first group and the second group, there is a difference of a CH2 group. Or to simplify it, we can obtain the members of a particular family by just adding CH2 moieties to it, or CH2 group to it. That is called homologous series, when two consecutive members of a particular series are differentiated by a CH2 group. Clear? Now that is the basic logic about homologous series. Now let us move to the next part of the topic, that is isomerism is the topic which we will discuss right now. After that, we shall discuss about nomenclature and the more, the more intrinsic part or the intense part of the chapter. But firstly, we will discuss about the topics which are basic building blocks to organic chemistry, right? So now, since we are done with a homologous series, we shall start off with isomerism. So the topic under discussion is isomerism. So isomerism. Now, first things first, we need to understand the meaning of the term isomerism. Now, isomerism generally means, or the meaning to it is, structures having, let me just write it first, then I shall explain it to you. Structures having same molecular formula, but different structural formula. Now, what do we mean by this? Okay, see, now to be very honest, if I do not use an example, it's very difficult to explain the definition to it. So let us take one example, that is, first of all, isomerism is of two types. Isomerism is of two types: geometrical and optical. Two types, alright? One is geometrical and one is optical isomerism. Now the second half to it, that is the optical isomerism, is something which we will learn in our senior classes, because it is a little complex compared to geometrical isomerism, right? Now, geometrical isomerism, the categories which we will study in class 10 is two. One is chain and one is positional isomerism. These two are our topic of concern, so as far as our board exams are concerned. Okay. Now, Now you might ask me, so ma'am, is geometrical isomerism only about chain and positional? No, it's not so. There are other isomerisms like tautomerism and functional group isomerism, metamerism, but that is not our topic of concern at the moment. Okay, so uh, one is now this thing is our topic of concern at the moment. Now I think uh, now, first of all, let us not classify isomerism as geometrical and optical. Let us make a broader classification to it. Let us make the classification as stereo and structural. Okay. Now, stereoisomerism would comprise of geometrical and optical. This part is not in our syllabus at the moment. Okay. And the structural isomerism would comprise of chain, positional, uh, tautomerism, metamerism, and functional group. But we are only concerned with both of these. Okay. Now let us start with chain. And I think by using examples, it will be easier to discuss the topic in detail. All right. So let us start. Now, suppose I have a molecule like this. So we are discussing chain isomerism. Okay. Now, now, suppose the molecule given to us under consideration is butane. Now, another thing. These names are not known to you. I mean, the foundation to the names, as in, how do we know that what is butane or how does this word but come from? I know, I accept, I haven't taught it as of now, but then that will be taught in the immediate next class. So don't worry. Just listen to the basic concept at the moment. Okay. So butane means an alkane comprising of 4 carbons. I repeat, butane is an alkane comprised of 4 carbons, right? So 1, 2, 3 and 4. And since it is an alkane, as we have just said, that all its hands are completed by single bonds and the bonds are made with hydrogen atoms, right? Now, what were we saying? So, butane is a structure having 4 carbon moieties, each of which has a single bond bonded to hydrogen. Now, chain isomerism basically means we have to change the chain in such a way that the formula remains the same, but the structure changes. Now, let's repeat once again. Chain isomerism is a kind of isomerism where we have to change the chain without altering the molecular formula, but just changing the structural formula. Okay. Now, since this is a linear compound, linear means a straight chain compound. So this is referred to as N-butane. This is the common name to it. Okay. That is N-butane. Why N? N stands for normal. Normal meaning linear. Straight chain butane. Okay. Now, if we have to write the formula to it, this is 1, 2, 3, 4, C4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So C4H10, this compound, is something which is shown in a straight chain form, right? Now we have to keep this formula intact. C4H10 has to be kept intact, but this structure has to change, which means this normal straight chain won't be there. You have to change this chain and create a new structure which will have this same formula. Now, how do we do that? Suppose if I take this branch, this CH3 branch, okay, this CH3 group, and attach it on the second carbon. Okay, now then the structure will become, so I am just removing this whole group, this CH3 group, and attaching it on the second carbon. So this is how it should be, completing the other hands by hydrogen. Now make sure that carbon should not have more than 4 hands. So that is very important. Alright. Okay, so I have just removed the CH3 group and attached it on the second carbon. Now see what happens. The formula to this compound remains the same. How? Number of carbon is 1, 2, 3 and 4. So it is C4. Number of hydrogen is 1, 2, 3, 4, 5, 6, 7 and here 3, 10. So this is C4H10. So the molecular formula remains unaltered. But what changes is this normal straight chain structure has become a branch structure. Let me repeat the word. It has become a branched structure. What do you mean by branch structure? That is, there is a hanging group apart from the straight chain. That is what you call as a branch. Okay. Now, when you have only one branch in a compound, that is referred to as iso group. Since this is one branch of the original structure butane, so we refer it to as isobutane. Clear? So the structure might have changed, but the molecular formula remains unaltered. Okay, so this is what is isomerism. And since we have changed a straight chain to a branch chain, we call it chain isomerism. Am I clear up till now? Okay, so let us take another example. Now, the second example which we will do is, suppose we take pentane. Now, one question I think might have arisen in your mind is, suppose, ma'am, in the previous structure, you have removed one CH3 group and created a branch out of it, right? So, what if I remove another CH3 group, suppose this one, and also attach it on the second carbon? So, what happens? Just a second, let me just remove this pentane part, otherwise there will be confusion. So, what did I say? I said, suppose we remove another CH3 group and create another branch out of it. So, what happens? See, now this group we have already removed and created a branch at the bottom of the second carbon, right? This carbon remains intact, this one right here. So this is next. And what have we done? This whole CH3 group right here, we want to attach it on the second carbon. Okay, so this is one CH3, this is one CH3, 1, 2, 3 hands. So this is the fourth hand, and for this carbon, there would be another 3 hydrogen. Now what happens is, if you say, ma'am, now we have 2 branches to the original structure, but this won't exist. Now, why do I say so? Okay. Why? Because there is a rule which we will learn when we do the nomenclature part or the naming part of organic chemistry. That is, you have to consider a branch keeping in mind that maximum number of carbons are present in the straight chain. I repeat, you have to consider the branch keeping in mind that maximum number of carbons are in the straight chain. Like in the previous compound, see, in the straight chain maximum carbon is 1, 2, 3 and then you have this branch, right? So the maximum carbon in the straight chain is 3. Correct? If you come to this structure, how many carbons can you keep in a straight line? Check very carefully. 1, 2, 3, these 3, or 1, 2, 3, these 3, or 1, 2, and 3. So 3 carbons are inevitably in the straight chain. And whenever you consider, whichever chain you consider, whether it is this one, 1, 2, 3, or this one, or the other way around, whatever you consider, you will see there will be one CH3 group that will be remaining as a branch. So there is no basic difference between these two structures. It's the same. So isomerism means you have to create a new structure. You cannot repeat the older structure. Since these two structures are the same, so this new structure right here is not possible. Right? Clear? Now let's move on to the next example which we were discussing, that is pentane structure. Now, since butane is 4 carbon, now the logical conclusion right now would be pentane would be 5 carbon, right? Because pentagon is a 5 carbon figure. So pentane would be a 5 carbon alkane. So let us first draw the 5 carbons and fill the rest of the hands by hydrogen, keeping in mind that the number of bonds for carbon should not exceed 4. Okay. Now, this is the structure. Now, this is a straight chain structure. So, we will call it as normal pentane, having the molecular formula C5, and number of H would be 1, 2, and 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Right? Now, let's repeat the same process. Take out one CH3 group and attach it on the center carbon, this one. Now, what happens? 4 carbons straight right there, and then one CH3 group, right? Rest of the hand would be filled with hydrogen. Okay, don't forget to do that. This is the thing. So since we have straight chain, we have 4 groups, 4 carbon moieties, and there is one branch. So this would be called as isopentane since there is one branch, but the molecular formula remains the same, C5H12. Now, for this particular compound, pentane, there would be another structure. See very carefully. If I take out the CH3 group and attach it on the same carbon right there, then what happens? So, 3 carbons are already there. This carbon already had a CH3 group and we have removed this CH3 and attached it below. Okay. Now, check what happens. So, the maximum number of carbons on the straight chain is 3. Like 1, 2, 3, this can be 1. Or 1, 2, 3, this can be 1. Or 1, 2, 3, this can be 1. Or it can be 1, 2, and 3. This can be another structure. So, maximum number in a consecutive straight chain is 3 carbons. So, the remaining 2 CH3 groups are branches. Since there are 2 branches, it is called as neopentane. 2 branch means neopentane. But the structure might have changed, but molecular formula does not change. That is why this is referred to as, this whole mechanism is referred to as isomerism. Clear? Now, this discussion is about chain isomerism. We shall move on to positional isomerism. Now, that is a far easier topic compared to chain isomerism. Both are easy, but if you want me to draw a comparison, then I would say that it is the easier topic compared to that of chain isomerism. So we are discussing positional isomerism, right? So now, what is positional isomerism? Now the topic itself is very clear. That is, position means the position of something has to change. Now, what do we mean by something? Now, position of something means it can be a bond, either a double bond, or a triple bond for that matter, or any group, okay, or any group like OH group maybe, okay, or any halogen group, anything of that sort, okay. These are the most asked topics of positional isomerism. Okay, so let's start the discussion. Suppose I take this structure. Now, as far as the nomenclature is concerned, I know you will not be able to do it because I haven't taught you. So let's just believe what I am saying right now. We can verify it in the next class, right? Whether I have rightfully said so or not. So this structure is pent 1-ene. 5 carbon and a double bond is referred to as pent 1-ene. Okay, now why so? In the upcoming classes we'll discuss. But just for the sake of discussion, let us just consider the structure. Now, pent 1-ene is having a molecular formula of C5 and H is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? H10. Now suppose I remove the double bond to the next carbon. What happens? 4 and 5. Now this might become, okay, now numbering suppose I do from this side. So that is why this was pentane and the one position had double bond. So pent 1-ene. So if we use the same analogy, then we'll see that this is also pent for 5 carbon and the position of the double bond is on the second carbon. So that is pent 2-ene. But the molecular formula remains unchanged. Check. CH3, H2, 1H, 1H and CH3. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is C5H10 again. But what has changed is the position of a double bond. This bond right here. Right? So now you might ask me that, ma'am, you have numbered it from the right hand side, right? Why couldn't we number it from the next left hand side? Now this is also a rule in the nomenclature part. But let me tell you, if we start numbering from the left hand part, then what happens is the position of the double bond is on the fourth carbon, right? Now, it's a rule that we try to take the position factor or the position number to be the smallest number and not the largest number. That is why we have numbered it from the right hand side and not on the left hand side. Okay. Now, let us move on. Try to shift it to the next carbon, the double bond, and see what happens. So this becomes C, C, double bond, C, C and C. So the position of the carbon, now you might say, ma'am, now the position of the double bond is 3. So this is pent 3-ene and this is the next structure. But I would say that you are wrong. Why? Because this might sound as 3 from here, but I said the numbering of the double bond should be the lowest number. So check, if we number it from the other hand side, which position does the double bond come? The second position. So this is pent 2-ene and not 3-ene. And we have tied the two structures on an equal level. So this is not a new structure anymore. We can follow the process of isomerism only up till the point when we get new structures. If at a point we do not get any new structure, that is the point we stop using the process of isomerism. Right? Okay. Now, I think that is about it, about the syllabus part of isomerism. So, I would like to leave a question for you guys so that you can solve it at home. And let me know in the comment section below. The question is, suppose I give you a structure like that. The name of the structure is, let me just say, this is but, since it is 4 carbon. But first position contains a triple bond and a triple bond is named as ine, Y-N-E. So this is a but 1-ine structure. My question is number of positional isomers you would get equal to how much? Okay, this is my question. Now, I would expect that you will do the homework and let me know in the comment section below how many isomers you have got. Okay. So I hope you liked today's discussion, and if you did, then please subscribe to the channel and hit the bell icon for more updates. Also, do not forget to like the video if you thought that it was necessary and it was good enough for you to score good marks in your exams. Until we meet in the next video.